Would you agree with me that all squares are proportional? Yes, because their angles all match up, right? We could say angle, 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 angle or something, I don't know. But they're proportional if all their angles match up. So these are proportional. So I could make ratios because they're proportional. Otherwise, I might not really care to do it because it wouldn't make sense. You wouldn't have sides that matched up, would you? If I look at this number 1 here, if I want the ratio of the sides, I could put the small, I'm going to always put my small one on top here and my larger one on the bottom. I'll just put big because it's shorter. So that would be 4 to 7, right? I can write it this way. I could write it 4 dot dot 7, but that's not as easy to work with. So I'm just going to make fractions because we can do that. Oh, this is the same one. No, sorry. Still on number 1, but now we're going to talk about the ratio of the perimeters. Yeah, 4 times 4 would be 16 on the small one, and on the big one, 7 times 4 is 28. But what does that reduce to? Ah, what do you notice about it? It's the same. That's because perimeter is a linear kind of measurement, and we say linear, it's because when we measure that in centimeters also, the sides are measured in centimeters, and perimeter is measured in centimeters. And what we're going to pay close attention to today is the exponent on our units. The reason that these are proportional is they're both linear measures. This one has centimeters, right? And there's an invisible 1 exponent on centimeters. And then down here, perimeter is also measured in centimeters, and there's an invisible 1. Now look what happens when we talk about the ratio of the areas. Yeah, if you know that it's just, this is a great figure to work with because it's easy to do these areas, isn't it? You square 4, you get 16. You square 7, you get 49. Notice that what this is 4 over 7 squared, right? What is your unit on area usually? Something squared, right? Area is a square kind of measurement. Really here, if I were doing this, this would be centimeters squared, wouldn't it? So the reason I took the side and I squared it is because area is a square kind of thing. They don't put this one on here, but I'm going to add another one because it follows also that if I were to do the ratio of the volumes, if I were to turn these into 2 cubes, that all the sides are the same. Yeah, 4 cubed is 64, and 7 cubed is 343, I think. And if you look at that, that's 4 over 7 cubed. Since the exponent on our unit is cubed, I would take the side ratio and I would cube it, and I could, get the ratio of their volumes. So we can use this to work some problems, and that's what you're going to see on this page. Let's flip over to the back just because there's some good notes to fill out over there that kind of solidify what we just saw now than it does to go do them in a minute. On the back, if you're looking, it says, so if the similarity ratio of 2 similar figures is A to B, which you could get this off the, just taking the sides and making a ratio. The ratio of their blank is A to B. That'd be the perimeter. That's the same thing as the sides. I'm just going to put that this is the side ratio up here. And so this would be, what did you say? Yeah. I thought you said something else. Never mind what I thought you said. I hope you didn't say what I thought you said. You probably not. I probably misheard that. Okay, so what ratio would be A squared over B squared? It's the area, because area is a square type of measurement.
The volume
Is cubed. So if you took it and you cubed the side ratio, you could get the ratio of the volumes. Now this is really useful because if you're talking about similar figures, you can make proportions and solve them. So we can use these ideas together with the proportions we've already done to figure out some things without having to do so much work. And one of the good reasons, you'll see in a minute that just having talked about area and also we're still talking about all these other things, volume, surface area, and stuff, that comes in pretty handy. So let's look at page. That was kind of like some notes to fill in. So we're back on the front now. Let's look at number 2. If I've got these similar hexagons. Oh, I don't like drawing these. I'm not very good at them. The area of the small one is 100 inches squared, and the area of the larger one is 169 inches squared. So what would be given what we've just talked about, what would be the ratio of the sides? And how did you get that? Yeah, you're thinking the ratio of the areas is 100 to 169, and you know that you square the side ratios to get that. So the square root of 100 would be 10, and the square root of 169 would be 13. What's the ratio of the perimeters then? Same thing, because it's a linear kind of measurement. It has an invisible 1 on the exponents. It's also 10 to 13.
So it's the same thing for the sides?
Yep, sides and perimeters are both linear things, so they would have the same ratio. They say the ratio of the areas, well, duh, they gave us that. It's 100 over 169. I actually already wrote it up here because that's what we had to use to solve the other two. Do I know what the sides of these things are? No, but I know what the ratio is, so, there's times I could use that to... this is kind of the same thing, I guess, if you think about computers and images and stuff. When you shrink, that's the same thing, shrinking a figure, what's the ratio of the two figures? You just keep that ratio the same as you stretch it. And its area is also going to change, but it's going to change at a different rate. It's going to change at the ratio of the sides squared. Okay, so let's see if I've got two rectangles. I do not know the dimensions, but I do know that this is 12 inches. And then on the larger one, I know the perimeter is 115 inches and the side is 15 inches. Now, I could solve for all the sides, No, actually, yeah, I could. I could solve for the sides in the larger triangle and do a lot of work, a little more work. And then figure out this perimeter over here if they're proportional. But I could also do this. Since the ratio of the sides are equal to the ratio of the perimeter, right? I could make a proportion, and I could put the side ratios on. What I'm going to do is I'm going to put my small one first, since they just put it first on the page, and then I'll put the larger rectangle on the bottom. So my side its ratio is 12 to 15. You can reduce that if you want to. Wouldn't that reduce to 4/5? Yeah, 4/5. So 4/5. And then over here, I'm going to look at my perimeter ratio because I'm missing a perimeter, and that's what I want to try to find here. So I'm just going to call the missing perimeter P, and it's on the small one, so I'll just put the P there. And this is 115. Instead of going and solving for the width over here and then using the width to make, figure out this other one over here, I can just do this, and I can cross multiply, and I'll be done. 4 times 115 would be 460, I think. Let me check that because, again, I'm not trusting the brain. I'm always surprised if it ends up right. Okay, that is right. And then this one would be 5p. Remember, we cross multiply when we have proportions. 460 equal 5p. If I divide both sides by 5, I'll know what the perimeter of the smaller figure is. 92, good, yeah. So that missing perimeter is 92. So it can help you work some problems faster, plus this is another one of those very possible for the SAT kind of things, because you see that this combines the idea of proportions with geometry. So, they always like to ask questions on these tests that measure more than one thing at a time, and it's a good way to do it here. Okay, let's move to number 4. We got hexagons. Not me, because, we have to go do the whole little right triangle, apophthegms, all that kind of mess, right? Not good times. Not good times, no. Actually, this says it's a hexagon, but it's actually an octagon. It is not a hexagon. That's a typo. I did not notice it till just now.
I've got the answer.
Do you? Oh, okay. Oh my. I do not know the area of the large one.
I do.
Megan thinks she does, but she's not correct in this instance. Now my side ratio, though, is 15 centimeters to 9 centimeters. So if I want to make a proportion out of this, I can use it to solve this area without having to do all that. If I were trying to find this area, wouldn't I have to go, first of all, figure out how big an angle in an octagon is? Then I have to draw my little right triangle, label it, and try to solve it. And it might not be pretty anyway. Here, it's not so bad because if I think about it, we're talking about area, so if I take my side ratio, what am I going to have to do to it to compare it to the area ratios? I have to do something to it. What kind of a measurement is area? What's the exponent on the unit? It's a square kind of thing. So if I square my side ratios, that would be equal to my area ratios. So my side ratios are 15 to 9, right? And I'm going to square them. Oh, let's reduce that, right? Who wants to square numbers, big numbers, when you can do small numbers? Let's see, that would be what? Yeah, 5/3. So that would become 5/3 squared is equal to the ratios of the area squared. We don't know the first one, so let's call it A. The second one is 45. A or 45, okay. So that becomes, if you square 5/3, that's 25 over 9, right? Okay, well, what equation can I make out of this? Just to make sure y'all understand these the way I think you do. 9x or 9a, I call mine A. Uh-huh. Is that what that is? Okay. I got 1125. Okay. Sometimes just easy to hit a wrong button. That's why it's always good, because if all of us are doing it and the majority of us get one thing, it's easy to kind of see probably what it should have been, right? And then just to find the area, you're just going to divide both sides by 9. You get 125? Is that what everybody's getting? Good.